What's up? Welcome back to Speed, Math, and CS. We teach APs, math stuff, CS stuff. Today we will be starting our study of AP Physics C, Electricity and Magnetism, and we will be starting off with Coulomb's law, point charges, electric fields, and potential. So now let's start with the first thing, which is going to be vectors versus scalars, right? This is the important thing in basically every physics course, right? So essentially all you need to know, right, is that a vector, right, well, there'll be some point, and then it'll basically lead to some other point, right? There will be a magnitude, and there can be like direction. Something like so, right? So, for example, velocity, right? Velocity will have speed, right, and direction. So now, if we think about a scalar is something that basically only has a magnitude. So, I already mentioned speed, right? So, speed is only it's only measurable. There's no like distance. So, for example, 5 mph, right? This is a scalar, right? Pretty simple. So now let's see how we can manipulate these, right? So the three things we'll be looking at first are vector addition, scalar multiplication, and vector subtraction, right? So let's start off with vector addition. So essentially what we will do is we will use this thing called the tip-to-tail method, right? So we will essentially take one vector. Let's say we're trying to add two vectors. Like, for example, call this vector A, and then call this one vector B. Essentially, to add these two vectors, we're going to convert this into a tip to tail. So like so, right? This will be A. And then instead, from here, we graph it going to B. So then overall, this will be our A plus B. So now let's go over scalar multiplication. And for scalar multiplication, essentially you are going to be taking a standard vector, right? Vector A, right? And multiplying it by some scalar, like vector A times 5, for example. This is actually pretty simple, right? All we have to do is essentially vectors are made up of magnitude and direction, while scalars only have magnitude, right? So we simply just multiply the magnitude of A, right? Magnitude, we use these absolute value bars to denote it, right? Multiply this by 5, and then we just keep the same direction. And I'll use A theta for direction, right? So it'll look something like this. And now, vector subtraction, we're essentially just going to use reverse tip-to-tail method, right? So reverse tip-to-tail method, essentially, if we're taking A minus B, right? If we're taking this vector and subtracting vector B, right? So we're trying to find what A minus B is. What we're going to do in this case, we're going to do reverse tip-to-tail. We're going to say, okay, A starts like this, and then essentially B is supposed to go here, right? But in our vector subtraction, we're going to flip it and say it'll go here, right? And then this going to this will be A minus B. So there you go. Those are basically the three types of manipulations we'll do with vectors and scalars. We'll also go on to seeing how you can multiply different vectors together and divide vectors together. But for now, let's start by going over coordinates, right? So there are two types of coordinates. The first type, right, is what we call polar coordinates, right? Say polar, right? Essentially, this is what we looked at earlier, right? We have some magnitude and we have direction. So, for example, 53.1 will be our direction, right? This is a polar coordinate. And then we also have another one, which is a Cartesian coordinate. Cartesian, or however you pronounce that. Cartesian coordinate, right? Essentially, here we will be using three unit vectors. I, J, and K with the arrow above, each signifying either X, Y, or Z. And then essentially, this will just be like, in terms of like, if we're starting at 0, 0, we're just going to represent this in terms of magnitudes. So in this case, if we're trying to represent this 5, comma 53.1 degrees, right? What we will do here is we will essentially draw out a triangle, right? We'll say, okay, we have this triangle. The vector is pointed like this, right? We have a vector A pointed like this, right? So magnitude is 5. You say this angle is 53.1. The Cartesian coordinate will be representative of its x and y. So what we will do is we will simply say this is 5. And remember, sine is opposite over hypotenuse. So it'll be 5 cosine 53.1 and comma 5 sine 53.1. Right? And essentially, this will simply equal 3 comma 4. Right? The other way we can do this is just Pythagorean theorem, but for the sake, this is how we're going to convert between polar and Cartesian. We're going to be using our cosines and sines. So now, let's go over the two products, right? Two types of products. Firstly, we got our dot product. Dot product, right? The way that this works is essentially to take the dot product, and the dot product, right? Think of this as like a return. It will be returning us a scalar, right? So in this case, the direction is completely useless. So if we were to visualize this, essentially if we have two vectors like this, A and B, right? To get the dot product, we want to simply choose one of the vectors, either A or B. In this case, let's just choose A. So we'll highlight this one. We'll highlight A. We want to see what parallel component B has to A. So in this case, we will have a parallel component like this, which we will call B parallel, and then we have a component like this, which we will call B perpendicular. And what the dot product says is that the scalar that is returned is simply A, B parallel, right? So the magnitude of A and then the magnitude of B parallel. So in order to derive this, we just have to derive B parallel. So we'll do the same thing. We'll basically enclose like a triangle right here. This is a triangle. And then if we have the magnitude here, let's let's define this as theta, right? If we have the length here, right? Let's say it's 5, right? Then in order to get B parallel, all we have to do in this case, we have opposite and hypotenuse. So essentially, this quantity that we said here, right? This is just AB cosine theta. And this is our dot product formula. This is how we calculate the dot product. Of course, we can do this in reverse as well, which in this case, it'll be BA cosine theta. But essentially, write this down, memorize it. This will be pretty helpful later. Although it might not have as many uses as, for example, a cross product, there are still plenty of uses for this dot product. So write it down, memorize it. Now, let's talk about the second type of product, right? We have what we call a cross, Well, we have what we call, a cross product. Cross product. So essentially, this one, right? Our return type will be a vector. So we will have a magnitude and we will have a direction. So in this case, what we will do is the cross product essentially is like basically sending a vector pretty much opposite, like the cross implies that it's opposite to the other two vectors. So in this case, right, we'll start by calculating magnitude, right? So we have a vector here of A, right? And then a vector here of B. So like earlier, we said we chose A. So then we're going to split B up into its components. So we have B parallel, which was here. Sorry, this is a little sloppy, but yeah. And then we had B perpendicular. In this case, because these two are perpendicular, assume A and B perpendicular are like perpendicular to each other. So they form the magnitude of the cross product, right? So the magnitude will be A, B perpendicular, which in this case, using the same derivation as earlier, will simplify to AB sine theta, right? So that's what our magnitude is. And now for the direction, we'll use an interesting trick, right? So essentially, regardless, or we can actually do this on the same diagram. We know that this A and B will fall onto some plane, right? Like assume that this what I just drew is like a planar surface and A and B are lying on it, right? Essentially, the cross product's direction will be drawing a perpendicular out from it. So this will be the cross product, A times B, right? Coming out of the same surface, A times B. And in fact, it'll start, actually I drew this wrong. So it'll start at the intersection. And essentially it'll come out of the surface, that will be your cross product. So essentially what you can do, just to help visualize this a little better, right? Let's say we have vector like this and vector like this, right? Which in this case, our plane is like right here. The cross product would then be like this, A times B. And of course, the cross product, like assume that this right here is our magnitude, right? So this will be much larger than the magnitudes of A and B. So yeah, now we have covered some background information on vectors and scalars. So now let's get into a concept that we'll call unit analysis, right? So unit analysis, essentially, we're trying to figure out if unit analysis can be used for two things. The first thing is that we will know what constants we need. So it can help us derive formulas. And second, it'll help us check if our answers are right. So later in this lesson, actually, we'll get into a formula, right? Where we say that delta V equals to delta U over Q, right? And then delta V will have the units of, let's say, joules over Coulomb. And then, so Coulomb, which is volts, right? And then delta U is energy, so it'll have units of joules. So now let's say charge will have units of coulombs. So let's say you forgot that if you forgot what goes on top. Let's say you did not know what was up here, right? Essentially what you could do is you could use unit analysis and essentially say, hey, the units of delta V are joules divided by coulombs, right? And we already have coulombs in a denominator. So we need to have joules in the numerator. So what has joules? Delta U. And we know it's delta because the delta also has to come from somewhere. So we can also derive that as well. So, and also we could use this to check our answers. So if the answer is supposed to be in some form, like let's say potential is in the unit volts, right? Joules over Coulomb. If we get, for example, joules over Coulomb squared as the units for our final answer, we know our answer is wrong and that we somehow divided a charge somewhere that we weren't supposed to. So now, basically the rules of unit analysis are that essentially, if we have multiplication, right? So for example, if you have 8 meters times 6 coulombs, right? This will combine into 86 meter coulombs, right? So the units combine here. And of course, if we're doing division, it'll go like this. It'll go 1 over. So for multiplication and division, the units just combine. You multiply the magnitudes, combine the units. For addition and subtraction, they have to be the same units, right? So for example, if you have 8 meters plus 6 coulombs, we can't do this. Like this is bogus. We just can't do this. Because how are we going to add a length to a charge? This doesn't make sense, right? So essentially, the only way we're able to add or subtract units is if they're in the same units. Like for example, 8 meters minus 6 meters, this is 2 meters. We know that, right? So now exponential functions are interesting, right? So they'll be in the form power equals to base to the x, right? So the base is the only thing that can have units. Only thing that can have units. Power, no units. No units for the power. And then the final answer, or actually, yeah, the final answer can also have units, right? But let's say the base doesn't have units. Let's say that it decides not to have any units. The final answer will also not have units. So now that we've gone over some of like the basic terminology that we need to know for the AB physics exam, let's get into actual like stuff. So because we've been talking about like this like the fancy details for a while. So let's first start with Coulomb's law. So Coulomb's law essentially is saying, hey, we have 2 point charges. We have a point charge here, that's A, right? And we have a point charge here, which is B. And essentially what this is saying is that the Coulomb's law is going to essentially tell us what the force will be that these two are attracted by or repelled by, right? This is what Coulomb's tell us, right? They'll be repelled and attracted by a vector, and Coulomb's law will give us the magnitude that they're attracted by. So essentially the formula for Coulomb's law is that force, right? Force has units of newtons, right? Force equals to the Q1 times Q2, right? Both of these we know will have units of coulombs, right? Divided by 4 pi E naught R squared, right? And R in this case is distance, which has units of meters. This E naught constant that is right here it's called the permittivity of space, and has units of c squared divided by newtons times meters squared, right? So if we do quick unit analysis here, we'll see that this lines up, right? So if we take, for example, our final answer needs to be in newtons, right? As we see here. So in the top, right, we will have 2 charges, right? So we will have c squared, Coulomb squared in the top as your units. 4 pi doesn't have any units. Permittivity of space, if we're dividing this by the way, we'll have c squared divided by n times m squared, right? So the c squared from the top will get canceled out, and in the top we'll now have n times meters squared. And then because this r has units of meters, that will cancel out the meter squared from the top. So we'll just have n. So we know that our quantity given by Coulomb's law is a force. And this is important. Understand that the concept we will get is a force. Now, let's do a quick practice problem, right? Based off of Coulomb's law, right? So, actually, it's fine. Okay, never mind. Let's move on to the electric field. So, we can do practice problems later. So, let's go to electric field now. So, for electric field, we will be using this first equation, right? Force will be equal to charge times electric field. Essentially, this means that force is the amount acted upon a charge Q in electric field E, right? So with this, essentially just to give a good idea of what electric field is, right? If we have a point charge, if we place a point charge in like somewhere in space and there's like other charges like around, this essentially says which direction will this get attracted to? Like, for example, if this was very strong, but like this is maybe more weak, it'll get attracted in this direction. So adding all of those up, what direction will we get attracted? Like we said, we could get attracted into this direction. So electric field will give us the magnitude of which direction we get attracted to. So essentially, we'll be using this equation, F equals QE. This is like a golden equation right here. Box it and memorize it. This is a very crucial equation, right? And essentially, what we'll be doing, as you notice here, right? The force has let's do more Newton analysis because it's important. So force has newtons, right? Q is charge, so C. So electric field, we now know electric field must have newtons per coulomb, right? So we know that electric field is actually a rate that compares newtons and coulombs. So now let's go on to the formula for electric field. So it'll actually look pretty similar to what we derived from earlier, where we'll have E. Yeah, so electric field will essentially be equal to, right, Q1, right? Essentially, where our Coulomb's law gave us newtons, this one will give us newtons divided by coulomb. So we're gonna miss a charge somewhere, and here is where that goes away. In this case, for electric field, we're just determining at any point what this newtons per coulomb will be. So in fact, this is not Q1. This can just be Q. But then after this, it's going to look very similar to the formula we had from earlier. 4 pi E naught R squared. Same formula. So with electric field, like I mentioned earlier, it can be in a space where there are many different points, right? So here is where we will introduce a concept of superposition, which will essentially say that if we evaluate the electric field, so it's better if we put like a subscript, E of n, right? So, and then in this case, it'll be Q of n. So we can essentially do this for all of this. We can apply this electric field equation, which is basically a corollary of Coulomb's law, right? We can apply this to every one of the charges in the space. So let's say we have like 6 charges, for example. Like we'll call them that's electric field. Let's say we have 3 charges, like Q1, Q2, Q3. What we can do is we can plug all of this into our formula, right? So we will essentially say, okay, we have a positive test charge that we're going to place, right? So for example, if we had these 3 charges, like here, 3 here, and then now we had we'll place like a test charge right there. So we'll use this to evaluate E of 1, E of 1, E of 2, and E of 3, right? And this will say, hey, for E of 1, we're going to just simply consider these two charges right here with our law here. So E of 1 will essentially say, okay, what is the charge of this? So the charge of this first one, of Q1, will be what goes into the numerator. And then 4 pi E naught, right? R squared. And, well, actually, yeah. So I forgot to go over what E naught actually is. So yeah, E naught will have a value of about 8.85 times 10 to the negative 12 coulombs squared divided by newtons meters squared, right? This will be the value for E naught. Sorry, I didn't go over this. I forgot. But yeah, so now for distance, it's simply the distance between these two charges. So between these two charges. There we go. So then now, essentially to evaluate the basically the direction that this red charge will go, we simply add E1 plus E2 plus E3. This is our principle of superposition. And essentially what we can do to visualize electric field is that in our system, right? Let's say this is our system, right? We can draw electric field lines. So we'll say these are our electric field lines. And basically along these lines, wherever you go, like if you have a charge here, these two charges, like this charge and this charge, will have the same electric field. All right. Now, let's get into the concept of electrostatic force, right? So, like I said earlier, the electrostatic force is a conservative force, meaning that the work done by moving a charge between 2 points depends only on the initial and the final positions, not the path taken. So, for example, this is basically we're starting on potential, right? So, if we started here, right, and moved toward this charge, we will travel through a potential difference. But it doesn't matter if we just go directly. For example, if you just go directly here, or if we take the super squiggly path to get here. The potential difference will be the same. So that is the first principle. So now let's try to calculate an energy function based off of our force. So in order to do this, right, we will basically have the function that f of x, or not f of x, f sub root x equals to negative du over dx, right? Where this is our delta u that we touched on very briefly earlier. So in order to solve for this, right, if we take the integral of both sides, right, we'll get that integral of force times dr, right? Or actually, if we move the negative to the other side, negative force times dr will be equal to delta u. So this is key. This is what all you have to memorize for this, right? And then u is the electric potential energy. So electric field is defined as the force per unit charge, right? So we already covered this. And the change in electric potential energy is what we have here, right? So delta U equals to the integral of force times dr. Or sorry. Okay, sorry. So change in electric potential energy will be equal, we'll say delta U equals to negative QE dr, right? Of course, we can take this Q out of the integral because Q is going to be constant. So now let's cover the electric potential and potential difference, right? So electric potential is defined as the electric potential energy per unit charge, right? So this is where our second golden equation comes into place, which will be work equals to QV. This, we can also have a converse equation where U equals to QV, right? These, we can use either of these equations, but this will be our second golden equation, number 2, right? So so Q, once again, so U has units of joules, right? Q has units of coulombs. So potential must have units of joules divided by coulombs, which we will define as a new one, volts. So now let's go over the electric potential difference, right? So in this case, what we can do is we can simply apply our formula from earlier, right? So we'll say that delta V equals to VB minus VA, right? So we're taking our formula from earlier, right? Let's say this is point A, this is point B, right? Our potential difference going from A to B is given by this formula, right? Delta V equals to VB minus VA. And this can actually be simplified to delta U over Q. And we already know that delta U is going to be equal. So we can actually do a further derivation with this. So we already know that delta U, we can take this yellow equation from up here, right? And then we know that delta U equals to negative Q of E dr, right? In this case, because we're going from point A to B, we will have a definite integral, A to B, divided by Q, right? Now we can just cancel these Q's out. And then now we have a relationship between potential and electric field, right? This negative A to B of E dr, right, is equal to basically our potential difference, this is equal to our potential difference. So this is an equation. So now we know potential due to a point charge, right, is we will have an equation based off of this, right? But remember that volts are in the unit joules per coulomb, right? So just for more unit analysis here, joules are equal to newtons times meters, right? So from earlier, the units for electric field were newtons by coulomb, right? Now it's joules per coulomb. So we've added a meters in the top. So if we take our Coulomb's law formula from earlier, we're essentially, in this case, right, we'll be getting joules. So volts, right? Volts equals to, we'll take the same thing, Q1 over 4 pi E naught. the way that we need a times meters in the top, but the way we can do that is actually by dividing a meters in the bottom. So this will actually lead us to a formula where we just have a single r this time, not an r squared. And this will be our formula for potential at a point. And once again, we can do the same thing I covered earlier with electric field, where you can take, for multiple points, find the distance E1 plus E2 plus E3. We can also similarly do V1 plus V2 plus V3. So superposition still applies here. So that's essentially what, like, this is all the, like, formulas we're going to cover today. So just like so like these are all the formulas we're going to cover today. So now we're going to move on to more conceptual things that should hopefully be easier to understand. Sorry, my mind was blanking there. But now we're going to move into conceptual things. So we're going to have, So let's learn about 3 different types. So there's going to be conductors, insulators, and semiconductors, right? So for example, if we have a metal ball here, right, and there's charges inside here, metal is a conductor. So this essentially means that the electrons inside of here are loosely bound and can move around really easily, right? So essentially, like, if I like, this is like electrostatic induction. So if I brought like a positive charge here, these would rearrange this is a positive charge, right? So all the positive charges will try to repel it, and all the negative charges will be attracted to it. So they will essentially split like that. Insulators, on the other hand, like, for example, if we had wood here, like, wood looks like this. This means that the electrons inside are locked in place, meaning they cannot move at all. So insulators are materials that resist the flow of electrons, and the electrons are tightly bound. So for conductors, some examples are aluminum or gold, and then for insulators, some examples are plastic, rubber, or glass. And then in between, we have semiconductors, which are metals with properties between conductors and insulators. So some examples of these are like silicon or germanium. And their conductivity can be controlled and are used in diodes, transistors, and solar cells. So like our solar panels and things like that. So yeah, that was a pretty long ride, but y'all made it through. So let's do like a quick review of all the equations we covered here, right? So these are all the important equations, right? Also, yeah, side note, if you made it to this point in the video, please give us a like and a subscribe. Like, clearly you're very dedicated in your E&M. You're in your E&M cells, so I'll just tell you that straight up. You are very dedicated. So, yeah. Here, in case you skipped to this point in the video, right, this will be basically a list of everything I would suggest, all the equations I suggest you would write down at the back of your notebook, right? We'll start off with our 2 golden equations. Mark them 1 and 1, 2, or sorry, we'll say our 2 golden equations. I don't know why I put 3. Yeah, our 2 golden equations, which will essentially say, the first one is force equals to charge times electric field. Force equals charge times electric field, right? This is how we get electric field. And then work equals to charge times voltage. Voltage is potential. Or energy equals to charge times voltage. Those are our two golden equations. And if you are going to go look at the homework later or go do practice, you'll see that so many of these problems will pop on where you'll be using these, right? So now the next thing is our force from potential energy. Or actually, first thing is now our 3 ways to get the distance between two charges. So first, Coulomb's law, right? We know that, so I'll actually do a quick thing here, right? And say that don't, just for like clarity, don't actually do this on the AP exam, but this is a way which you can simplify your work. Essentially say, we will define a variable k, which is equal to 1 over 4 pi times the permittivity of space. And we can assume that this is 9 times 10 to the 9th, right? And the units for this will be directly opposite. They will be newtons times meters squared divided by coulombs squared. So using this k, let's define Coulomb's law this way, which will simply be k q1 q2 divided by r squared will be equal to force, right? There's our force equation for Coulomb's law. And then now kq divided by r squared, that is our electric field equation, right? And then now kq divided by r, we removed another r, and this will now be our potential equation. These 3 equations are also important, right? So, yeah. And then now the relation between electric field and potential. This is how we go between electric field and potential. So I'll mark this as a red, right? So electric field equals to negative dV over dr. That is the equation, right? And yeah. So I think these 6 equations, I'd say if you memorize these 6, right, the ones I say here, F equals QE, W equals QV. Know those 2, like top of your head. First thing when you see a problem involving, like, let's say, okay, we have charge as it passes through a potential difference. How much work does it take for a charge to push through a potential difference? As soon as you see that, you should be W equals QV right there and there. Same thing if we see how much force does it take to push a charge through an electric field of this much. F equals QE should instantly pop in your head. Those 2 are our golden equations, right? Now, these 3 are essentially variations of Coulomb's law, but to calculate force between 2 point charges, electric field at a point, and potential at a point, right? So k q1 q2 divided by r squared, kq divided by r squared, and kq divided by r. Also, on the actual AP test, k will actually be equal to this. So make sure you write this, but this is just so you remember this equation easier. The k helps simplify all these variables, which just simplify to a constant. So, and then lastly, know how to go from electric field to potential. E equals negative dV dr. Wow, that was a lot. Hopefully you guys understood. Hopefully you guys got a good grip of the Coulomb's law, electric potential, electric field, and point charges. So we'll see you soon, and hope you subscribe again, show us some support, and we thank you for watching this video.